Smells so good in here. Can you smell it?
No.
You can smell it? You can smell it?
I can smell it.
You can smell it. Can you?
Oh, I can smell it.
Oh, now you can smell it? Anna, can you smell it?
Oh, are you doing it?
Catherine?
This is part of the thing.
Oh,
Guys, this is part of
you can't smell it?
I thought you were I thought you were like disinfecting.
This is definitely part of the lesson. No. Can you smell it yet, Anna? Oh, man. But Peyton, you definitely smelled it before they did. Yeah. Okay, so have you ever noticed, maybe now you know I wasn't disinfecting you, but it can take a while before you notice the smell filling a room. And when we think about gas molecules, they're actually moving ridiculously fast, hundreds of miles an hour. And so in theory, I mean, they should move faster than the speed of sound oftentimes. And so if gas molecules were really moving unimpeded, they would diffuse very, very quickly. But there's actually a lot of gas molecules, and they can't make a direct linear path from like me to you. And so they kind of diffuse and spread out, but there are other ways to kind of detect it. What I just did was I basically put a drop of food coloring in the air, and it just dispersed, but it was the air freshener because our noses can detect it even through the mask. I usually don't spray that much, but we're wearing masks, so that's why I put that much. So question is, can we calculate that? Can we measure that movement, particle movement of gases? And we can. It relates to what's called Graham's law. So diffusion is the process in which particles in a system move from an area of high concentration to an area of low concentration. This concept gets taught in a lot of different ways, and it can be dealt with in a liquid form. It can also be dealt with in a gaseous state. We're talking about it specifically with gas molecules. But it all has to do from a particle model of particles in motion. It will continue, that air freshener or whatever will continue until there is a uniform concentration of particles and it's reached throughout the whole system. And our noses can really only detect changes in smell. So that high concentration, you get that nice whiff, which is why you detect it. But then as it diffuses, the amount of those air freshener particles entering your nostrils is less per unit volume of that inhale. And so your brain doesn't detect it or doesn't register it because it's not that different than what the air smells like. At constant temperature, so what Graham's law states in words is that at constant temperature, so in this room, if the temperature remains the same, the rate at which gas molecules diffuse decreases as the molar mass of the gas increases. It's an inverse relationship. Said another way, small things move fast, big things move slow, or relative to each other. Okay, so another way of saying this, the rate of diffusion is inversely proportional. I don't like writing out the word proportional. The symbol is much better. To the molar mass is another way of saying that. So the bigger the gas molecule, the slower it moves. The smaller the gas molecule, the faster it moves. And it's proportional to the molar mass, which is nice for calculations, okay? Because it's like if something is twice the size of something else, it moves at half the rate. So it makes it easy to calculate that. Let's see here. So it is inversely proportional. I do like to point this out. It's not linear. It's 1 over x, not negative x. It will have asymptotes. You can't have like less than 0 particle movement. Okay, there is an absolute to it. There's a maximum speed that could be reached before you then like strip the gas molecules of their like ability to be gas molecules, and then they move into the plasma state, etc. Stuff like that. Okay, but it's an inverse relationship there if you were to plot it graphically, just as a way to think about that. Okay, so if you want in the reading on this one, it does go into the derivation of it, but a little bit more than what I need you to. If you're interested in it, it will talk about other things. But if we think about two different gases at the same Kelvin temperature, so that means they have the same kinetic energy, since temperature is a direct measure of the average kinetic energy of particles. So we can then set in an equation form, we can say, okay, the kinetic energy of gas 1 is equal to the kinetic energy of gas 2. That does not mean that they're moving at the same rate, but they have the same amount of kinetic energy proportional to each other if they're at constant temperature, okay? Does anybody remember the equation for solving for kinetic energy? Yes, 1/2 mass times velocity squared. And that can be mass of gas 1 and velocity of gas 1 is equal to 1/2 the mass of gas 2 times the velocity of gas 2 squared. You can set them equal to each other, all right? Not that you need to do this, but I'm just trying to show you that if these are equal, if the mass of one is larger than the other, okay, so this one's lower, for these to be equal, then the velocity of this one has to be proportionally lower, and the velocity of the second one has to be proportionally higher, okay, since they're set equal to each other. So a gas like hydrogen, which has a pretty low molar mass, can move significantly faster at the same Kelvin temperature than something like carbon dioxide, which has 22 times the mass, so it's going to move proportionally slower. You follow? Okay. It's a range. Okay, I think I said that. Yes. Now, if you rearrange it, I'm not going to. I mean, you can get rid of the halves. You can take the square root. You can move the masses over. But the equation that gets used to set a proportion for Graham's law is it really. Okay, we'll go here. So the velocity of one gas to another is equal to the square root of, it's the mass, but we'll use molar masses here, of one to the other. But notice that they get flipped because they're inversely proportional. And so the way you'll see Graham's law written, and the version that you need, is the rate of diffusion of gas 1, simplified this way, rate of gas 1, or I'll do A, over the rate, how fast it's moving. Rate, usually we can do a velocity, or it can just say it moves at a certain speed without the direction. They can give it to you in some kind of measurement, okay? And the rate of one gas proportional to the other is equal to the square root of the molar mass of the second one over the molar mass of the first gas there. Depending on what you're going to solve for, you can determine unknown gases this way. You can predict the rate of gases just by knowing what gas it is if you know the temperature, etc. But this is the form of the equation that you see in textbooks around Graham's law for chemistry class. But it has to do with the derivation and understanding of kinetic energy, and that when you have gases in the same temperature, proportionally, they move at a rate inversely proportional to their molar mass. Yes?
So does that mean that the rate of diffusion is in meters per second?
It can be in meters per second, it could be in centimeters per second, it could be in miles per hour. And that's why I say rate, like it's some velocity measurement, and it just kind of depends. You'll see in Graham's law problems, you know, they could have it in nanometers per microsecond, like, you know, whatever makes sense for the whatever device is measuring the movement of the gases. So but it honestly doesn't matter what the units are for the rate, because they're going to cancel each other. So you're going to end up getting a numerical value that if you know the two gases, you can just plug in their molar masses. You will get some number. That number will be over 1. Whatever gas you put on top, whether if it's smaller, you'll have a proportion where it's moving at a rate greater than the other one. And if it's a number less than 1, then it's telling you it's a bigger gas and it's moving at a rate slower than the other one. But with Graham's law, you're comparing how fast something is moving relative to something else. So it's always giving you a comparison value, which you're going to see tomorrow in the lab. So we're going to put two gases in a tube, and they are going to move. And you're not going to see them move because, well, they're invisible, okay, to our eyes. But when they meet one another, they have a chemical reaction that forms a visible ring, precipitate reaction that occurs. And we can see where they moved. And if we put them both at different ends of a tube, a long glass tube, if we put a gas in each end of the tube and see where they meet, so maybe they meet in the middle, then they're similar molar masses. Maybe they meet closer to one side or the other. You're visibly seeing how fast they move relative to the other one. And then we can use that. If we start the timer at the same time, the distance that each one moves relative to the other one in the same amount of time, we can then calculate the relative rate experimentally to what we would expect theoretically, if that makes sense. Just a quick little thing on diffusion versus effusion. So I did call this Graham's law. I don't remember now in the title. Some years I name it diffusion, some years I name it effusion. But both are processes. It's just like a vocab thing where particles move from an area of high concentration to low. But diffusion is in all directions. If you have effusion, that's technically directional. So if you had a pinhole leak in a balloon or a pinhole leak in like a tire, then you're having the gas effuse because it's being forced from an area of high concentration, like in a pressurized tire, to an area of low concentration out here in the atmosphere. But because it can only go one way, it's called effusion. But if things can go both ways, so like in the lab that you're doing today, you have a problem where you open a canister and the gases can move both ways, it's the bonus question, then that would be diffusion because the gases can go in both containers. It's not one way versus the other. It's just a vocabulary thing. You can call someone out if they use the word wrong. You know, biologists like to call things diffusion a lot and it's really effusion. It's fine, whatever, okay? There. But if you give particles enough space, then they will move out in all directions. It's just if you force them through a narrow hole. Like tomorrow, if we're putting gases in a tube, are we going to be defusing them or effusing them? Yeah, we're forcing them down one direction until they meet. Because they really can't go out the other way. They'll be forced to go. So it should be called Graham's law of effusion tomorrow, but it's not. Tomorrow we will do the lab and collect data. I haven't done any